Dear friends, welcome to the 17th video lecture of our differential geometry course. Today we will cover so-called Gauss-Bonnet Theorem. Let me state the theorem and then we will sketch a proof. If sigma g is a compact genus G surface in R3, then the integral of the Gaussian curvature over the surface with respect to the surface area element is equal to 4 pi times 1 minus g. Okay. So this is you see the right hand side is a topological invariant, and what we see is that the sum of the geometrical invariants over the whole surface is just the topological invariant. So here where Kp is the Gaussian curvature of sigma g, and ds is the area element on sigma g. Let's see the proof. We will not give all the details of the proof. It is not actually possible to do that in the content of this course. We will make some assumptions. Some of the things we will assume are actually proved in the book, but in later chapters. However, we don't have time to cover all these, so we will just assume those. There are actually two important facts we will assume. One of them is a topological fact. So let me just start with that topological fact. So we will use a topological fact as follows. Let sigma g, the surface above, be triangulated so that the triangulation has V vertices, E edges, and F faces. Then the integer V minus E plus F is equal to 2 minus 2G. So this alternating sum is independent of the triangulation. And this number is called the Euler characteristic of the surface sigma g, and the notation is this notation. We will denote this number with this notation. chi of sigma g, Euler characteristic of sigma g, is just 2 minus 2g. Let me explain this on an example. I'll do just one example. Consider, for example, the tetrahedron. Okay, so this tetrahedron has what? Number of vertices: 1, 2, 3, 4 vertices. Number of edges: 1, 2, 3, and then 3 above, so 6. And it has 4 faces. It's a tetrahedron. And you see that this is actually homeomorphic to the two sphere, right? It is just two sphere, just whose sides are just planar. Okay, and this is a genus zero surface. So Euler characteristic of sigma g should be 2 minus 2 times 0, which should be 2, and it is really v minus e plus f. 4 minus 6 plus 4, which is just 2. Okay, so this is one simple example. Okay, also we need a geometric result, which is about Gaussian curvature, and it is the following. Let T be a triangle on a surface so that its sides, its edges are geodesics. Geodesic curves on sigma. Then the conclusion is this: the integral of the Gaussian curvature with respect to the area element on this triangle is just theta 1 plus theta 2 plus theta 3 minus pi, where theta 1, theta 2, theta 3 are the interior angles of T. This is a deep fact. It is not easy, but we will assume it because we don't have time to prove this result. This result tells us the following. Suppose that we have a surface, let's say, like this. Okay. And suppose we have a triangle here. A triangle whose sides are geodesics. Okay. So like this. And let's say the angles are like this: theta 1, theta 2, theta 3. Theta 1, theta 2, theta 3. Then if you integrate the Gaussian curvature over this triangle, what you will get is sum of these triangles minus pi. Okay. One actually obvious example is the following. Let me do another example. So this is one example. Sorry. Another example is this. So let's take our surface. Here, the surface has Gaussian curvature negative, and you see that the angles, the sum of the three angles, is less than pi actually. But if you take a plane, usual plane, and then take any triangle, well, we know that the sum of interior angles is just pi, of course, right? And that's not a surprise, of course. The Gaussian curvature is zero, therefore the integral uh, is zero. So let me see. Okay, these angles, theta 1, theta 2, theta 3. So theta 1 plus theta 2 plus theta 3 minus pi is 0, of course. And this is, of course, not a surprise because the integral of the Gaussian curvature is 0 because Gaussian curvature on the plane is identically 0. Okay. Another example, let's say uh, we have a sphere of radius, let's say r. Okay. So sphere of, okay, let me write like this. A sphere of radius r. We know that the Gaussian curvature at any point is just 1 over r squared. 1 over r squared. So if you take a triangle here, let me take triangle like this, starting from the North Pole. I take two geodesics, great circles, and join them like this. So theta 1 is this angle. Okay. Theta 1, theta 2, and theta 3. Actually, theta 2 and theta 3 are 90 degrees. So the sum of the angles, theta 1, theta 2, theta 3 minus pi is the if this is the triangle T, we take its integral, ds. This is just constant function 1 over r squared. So 1 over r squared goes out, and then I integrate ds, but this is just 1 over r squared times area of T. So what we see from this, also this is just pi. So what we see is that uh, theta 1 times r squared is equal to area of T. So this is a very nice result. If you have a sphere of radius r, and if you have a geodesic triangle like this, then you can find the area of it by just computing the angles. And in this special case, if these two angles are just 90 degrees, then the area is just given by r squared times theta 1. All right. Now we will make use of these two facts in the proof of Gauss-Bonnet theorem. Okay. All right, back to the proof. Well, so this is my surface sigma g. It has genus G. So and let's take a triangulation of this uh, surface. So let me say, we have a triangulation like this. Let's say this is TK. Suppose these are just some geodesics. And so, okay. So let's say this is vertex VI, this is vertex VJ, and this is HEL, and this is triangle TK. Okay. All right. Now, uh, so take a geodesic triangulation of sigma g uh, with uh, v vertices, e edges, and f uh, faces. Okay. Then of course we know that. Then we know that v minus e plus f, which is the Euler characteristic of this, is equal to 2 minus 2g. Okay. Now let T1, T2, TF be the list of all triangles in the triangulation. So this is TK, for example. Okay. Well, since sigma g is the union of TI's, okay, we have this sigma g is equal to T1 and TF. Okay. Let theta I1, theta I2, theta I3 are the be the interior angles of the triangle TI. Okay. Then we have the following. Now we have the following. Integral over sigma g kp ds. Well, this surface is the union of these triangles. So integral over this is equal to the sum of the integrals over each triangles. So this is from, all right, let me write it this way. All right, instead of this, let me write union ti I from 1 to f kappa s kappa p ds, but this is equal to summation, since these are uh, interiors of these triangles are disjoint, only on the boundary curves they intersect, and that doesn't uh, make any change in integration, so I can consider them as disjoint, and in that case this integral becomes what? It is just the sum of the integrals over each triangle. But here triangles are geodesic triangles. Therefore, each of these integrals are just sum of the interior angles minus pi. All right. I have f many triangles, so I will have the following: minus f times pi plus theta I j's, right? I from 1 to f, 1 to f, and j from 1 to 3. Well, what is this? Well, you see, the interior angles are like this, right? I mean, this is one interior angle, this is another one, and then there will be probably another one and another one. So at each vertex, the sum of the uh, interior angles of the triangles will be 2 pi. Here again, the sum will be 2 pi. Here it will be 2 pi, and so on. So the sum of the triangles, sum of the angles uh, of the triangles will be how much? It will be 2 pi times the number of vertices, because at each vertex this interior angles add up to 2 pi, and we have v vertices. So this is the sum of uh, all interior angles, and it is just v times 2 pi. Okay, so here let me make a remark. You see, this gadget is just sum of the all interior angles of all triangles, and that is just number of vertices times 2 pi. All right, what else? Okay, finally we make the following observation. Moreover, each triangle each triangle has 3 sides, and every edge in the triangulation is the edge of exactly 2 triangles. Hence, we see this 3 times f is equal to 2 times e. Okay, because every triangle has 3 edges, and every edge is the edge of 2 triangles. Okay. So this integral which is equal to minus f times f plus 2v pi 2 pi v, right, can be written as follows. In 2 pi parentheses, this is v minus e plus e minus f over 2. Okay, I can write it like this. See, I added e and minus e, so it gives me 0. I get exactly this gadget. But then I make use of this identity here, and that tells me what? E is equal to 3f over 2 minus f over 2. So that gives me 2 pi times v minus e plus f. So 2 pi times the Euler characteristic of sigma g, which is 2 pi times 2 times 1 minus g, or 4 pi 1 minus g. And that's uh, what we wanted to prove. Okay, exactly the statement of the theorem. All right. Uh, as I said, here we made two important assumptions. One of them is topological, about the Euler characteristic. Uh, that's not an easy fact. Actually, showing that every smooth surface has a triangulation is not a trivial fact either, but we assume those. Uh, Otherwise, we cannot prove the theorem. And the second fact actually is proved in the book. It's a geometric fact, but it is proved in later chapters, and we don't have time to cover that. Later, I will put another video which is about an alternative proof of this theorem. It uses some other facts, again, which are not covered in this course, but it's an alternative proof, and that one doesn't have actually any gaps in it. I'll do it later. So for now, I'll stop here. See you all later.